students. Today we discuss about how to explain work energy theorem in different situations. How to apply work energy theorem in different cases. Now we can explain first case, case 1. So in the case 1, if you consider a body of mass m, it is projected vertically upwards with initial velocity u. Now this body reaches to maximum height. So here the body of having final velocity at the position maximum height, here its final velocity 0. So here initial velocity is u. So now work done by the gravitational force in this situation, according to work energy theorem, work done by the gravitational force is equal to, according to work energy theorem, W equal to change in kinetic energy. So now in this situation, here Wg, that means work done by the gravitational force equal to change in kinetic energy, means final kinetic energy minus initial kinetic energy. So here Wg equal to, here final kinetic energy 0, because here at maximum its velocity 0, so therefore final kinetic energy is 0, minus here initial kinetic energy is of mu square. So therefore Wg equal to, in this situation, work done by the gravitational force equal to minus of mu square. So this is the case 1. Now we can explain case 2. Case 2. In the case, we consider a body of mass m, it is freely fall from certain height h. So now it reaches the earth surface, its final velocity is v. So here initial velocity of the body is u equal to 0. So its position is h from the earth surface. So now in this situation, work done by the gravitational force is mgh. So now work done by the air friction. So now we can find out the work done by the air friction is in this situation. So now according to work energy theorem, total work done in this situation is equal to change in kinetic energy. So in the case of total work done, means there are two work dones, that means one is work done by the gravitational force, another one is work done by the air friction. So Wf, so equal to final kinetic energy minus initial kinetic energy. So in this situation, work done by the gravitational force is mgh plus wf equal to, here final kinetic energy is of mv square minus initial kinetic energy is 0 because her body is freely falling. So in the case of freely falling body, initial velocity is 0. So therefore work done by the air friction Wf equal to half mv square minus mgh. So this is the work done by the air friction in the case. Now case 3. So in case 3, if we consider a smooth inclined plane of inclination is theta, its height is h. Now if we consider a body of mass m, it is one of the block is freely fall from top of the inclined plane. So here initial velocity of the block is 0. So it is a smooth inclined plane. So now this block is sliding downwards. Now it reaches the bottom of the inclined plane. Its velocity is v. Here capital V is the final velocity of the block at bottom of the inclined plane. Here u equal to 0. Its initial velocity of the block at the top of the inclined plane is 0 because it is a freely fall. So now we can find out the final velocity of the block at the bottom of the inclined plane. So in this situation we can apply work energy theorem. According to work energy theorem, W equal to change in kinetic energy. So in this situation W equal to, so here work done by the gravitational force, that means Wg equal to, so here change in kinetic energy, that means final kinetic energy minus initial kinetic energy. So Wg equal to final kinetic energy means of mv square minus, here initial kinetic energy 0 because when the block is freely fall, so initial velocity of the block is 0. We know that work done by the gravitational force Wg equal to mgh. So here h is the height of the inclined plane. So therefore mgh is equal to half mv square. Here mm are cancelled, so therefore v square equal to 2gh. Now velocity of the block at the bottom of the inclined plane v equal to root over 2gh. Right. Next, case number 4. Case 4. In this case, if we consider a simple pendulum of length L, its mass of the bob is small m. Now a force is horizontal force acting on the bob, its velocity, horizontal velocity is v. Now this bob is rises certain height h. So here, so this is the height h. Now here L is the length of the pendulum. So now it is making an angle theta with the vertical direction, that is the theta. So now its value is L minus h. So this one. Now height of the pendulum, that means it rises a certain height, it's you can calculate the height h. So cos theta equal to h inside L minus h by hypotenuse L. So therefore L minus h equal to L cos theta. So therefore h equal to L into 1 minus cos theta. Now in this situation we can apply work energy theorem. So that means W equal to change in kinetic energy. So in this situation, work done by the gravitational force Wg equal to Ke final minus Ke initial. So in this situation here, initial velocity is v. Now at that position, its final velocity is v1. So now work done by the gravitational force, that is the mgh, is equal to, so final kinetic energy is of m v1 square minus initial kinetic energy is of m v square. Here v1 is the final velocity of the bob, here v is the initial velocity of the bob. So now in this situation here h equal to L into 1 minus cos theta. Here L is length of the pendulum. What is length of the pendulum? It means it is the distance between suspension point to the center of the bob, that is the L. Here L is the length of the pendulum. So therefore mg, here h means L into 1 minus cos theta is equal to half m v1 square minus v square. So in this situation, when the bob is rising upward direction, so acceleration a equal to minus g. So in this situation a equal to minus g. So now here a equal to minus g, that means minus mgl into 1 minus cos theta equal to half m into v1 square minus v square. So this is the case 4. Now we can explain case 5. Case 5. So in the case, it is one of the wooden block. Now if you consider a mass of the bullet small m, its initial velocity is u. Now this bullet is penetrating to the wooden block. So now when the bullet is penetrating some distance, then it is at rest. So that means here final velocity of the bullet is 0. So now it is penetrating some distance x. Now here resistance is offered by the resistance force is offered by the block to the bullet. So this direction is capital F is the resistance force offered by the block to the bullet. So now in this situation we can apply work energy theorem. So therefore W equal to change in kinetic energy. So in this situation here W equal to force into displacement. In this case F into here displacement is x. Now this work done is a negative work done, because here resistance force is in backward direction, displacement is in forward direction. So therefore the angle between force and displacement is 180 degrees. W equal to Fs cos theta, cos 180 equal to minus 1. So therefore its work done is negative. Minus F into x equal to, here final kinetic energy minus initial kinetic energy. So in this situation, final kinetic energy is 0 because here final velocity of the bullet is 0. So now minus F into x equal to 0 minus initial kinetic energies of mu square. So now minus minus cancel. That means F equal to half into mu square by s. Here F is the resistant force offered by the block to the bullet. Okay, thank you.